Hi, and good afternoon, everyone. Welcome to the Learning Tree Machine Learning and Text Analytics webinar presented to you today by Learning Tree author and instructor Dan Busker. Thank you so much for joining us. Before we start, I want to take a moment and introduce you to the Learning Tree Anywhere platform. If you've ever participated in a Learning Tree class as a live virtual attendee, you will recognize this layout as this is what we use in our Learning Tree courses. So you'll see our presenter, Dan. He's in the upper left-hand corner there of your screen. Below Dan is our chat box, and this is where you can participate with questions or comments or saying good afternoon from all over the country and the world. And then in the top middle, you'll see the presentation. Below that are some poll questions if you want to take a moment and answer the poll if you haven't already. I'd love to know a little bit more about you. And as I mentioned, you can see our presenter Dan there and tell you a little bit about Dan. He's been a Learning Tree author and instructor for over 14 years now and knows a little or a lot about everything. In addition to his profession, in addition to his profession, data and analysis work, Dan is a proponent of functional programming techniques in general and really enjoys speaking at users groups and webinars like he's doing for me today. So thanks, Dan. And if you want to go ahead and take it away, sir, I'd appreciate it.
Alrighty, well, I know you didn't sign up to look at me, so let's move on to the next slide. Um, we're going to start out just with a crude classification of some various types of techniques. These are categories that are gray around the edges, but it will help us kind of understand how things evolved and how we got to the world the way it is today. Text analytics has actually been around a lot longer than a lot of people appreciate. Literally for hundreds of years, people have argued about things like whether Alexander Hamilton or Thomas Jefferson wrote a particular document, or whether some poem was Christopher Marlowe or William Shakespeare. These are examples of what's called stylometry. We won't be talking much about that, but it might interest you to know that that goes back to at least 1439. A fellow named Lorenzo Valla did a text analysis in order to demonstrate that a particular important document of the church was in fact not genuine. It was a forgery. Back then, the computers they used were about as accurate as we have today, though considerably slower and with much less RAM. Oops, you'll see that from time to time. That's me being clumsy and leaning up against the touch screen. I'll try not to do it. It's really library science and document relevance that's important on this particular slide, because it was the development of methods for library science that created many of the techniques that in fact are still being built upon today. I'm going to mention supervised learning just in passing. Supervised learning is important for things like spam detection. I know I'm very thankful for spam detection, but it's important to realize that in general, many supervised techniques do not involve any sort of serious understanding of the text. There's no attempt to read the words and discern their actual meaning. When we talk about supervised learning, we're talking about machine learning that operates on a set of historical data where human beings have sat down and already characterized it, and that pile is the spam pile, that pile is the legitimate email pile. Once they've been categorized by human beings, it's simply a matter for the machine learning algorithms, whatever the developer might choose to discern correlations among the words and so forth. And some correlations may be strong for spam, others stronger in legitimate email. Our primary topic today is semantic analysis. In semantic analysis, one is actually trying to make some attempt to get a digital handle on what documents actually mean. This, of course, is the most challenging, but it's also the most rewarding in many senses, including the financial sense. Chatbots are big business. Everybody's heard of Alexa and Siri. You may have heard of Xiaodu. That's the version given to us by Baidu, the Chinese internet giant, which is actually a major contributor to developments in this area. Machine translation is extremely important. And though the phrase is not so widely recognized, a lot of what we talk about today will be relevant to so-called topic modeling. Originally, when people started doing research into library science and document relevance, they were simply looking to see whether words were present in particular documents. Topic modeling falls a little short of true semantic analysis, but what it tries to discern is what the document is about. Obviously, you can infer some of what a document's about by the words it contains, but traditional searches have not really allowed you to search for a document by topic. They've only allowed searches by keyword. Now, fortunately for us, the data preparation techniques have not really changed. We're always starting out by defining what we mean as a document. This may be a Wikipedia page. It might be an SMS text message. That's going to depend on our application. But what we do to these documents is always going to be the same. We're going to have to chop it up in some way into digitally bite-sized pieces. Now, traditionally, documents have been reduced to what a lot of people call bags of words. Bags of words has the advantage of being easy, but it also jettisons a fair amount of meaning. For example, if the document contains the phrase "Leroy likes Mary," and you chop up the document into individual words, well, Leroy is going to be in that pile of words, as is Mary, but the obvious relationship, Leroy likes Mary, is lost forever once you break up the document into individual words. In a moment, we'll talk about n-grams. These are small sets of words as opposed to individual words. And as computers get faster and RAM becomes cheaper, it becomes more and more practical to use n-grams to solve the problem of Leroy liking Mary, and maybe Mary not reciprocating those feelings. We won't talk much about stop words. This is fairly obvious. In English, we have articles like and the. And even though these contribute meaning to a sentence, you know, a book is not the same as the book. Nevertheless, they don't contribute enough meaning to be considered worthwhile attending to for many of our techniques. And then, of course, there are many words that have multiple forms, particularly in English and other Western European languages. And we would like to reduce these to a single form for purely practical reasons. As I mentioned, as RAM gets cheaper and people have bigger, more powerful computers, it becomes more and more practical to start paying attention to sets of words like, trigrams and 5 grams and so forth. While we won't be discussing these in this short session we have together, it's worth mentioning that exactly the same techniques can be applied to units other than words. We could apply it to phonemes, we could apply it to syllables, we could even apply it to base pairs of DNA. I'm going to momentarily switch over to a virtual machine here, and for some reason that rectangle shouldn't be there, but I can move it out of the way. Okay, and my aging eyes are having trouble picking up the right tab there. I apologize for that. Actually, one of the most important things here is the Python library that we're using to process the n-grams. NLTK, or the Natural Language Toolkit, is one of the older libraries that's been available to Python developers. In fact, this year it's celebrating its 20th anniversary. We're simply going to use it to illustrate the idea of n-grams. So I'll import the library. We'll start with a trigram. And it's important to notice that we're not breaking up the sentence every third word. When we say trigram, it's every set of 3 contiguous words from the sentence. So we start out with this is the first 3 words, and then the next trigram is a foo, and then a foo bar, and so forth as we march through the document. It's clear that if we do this, our demands for computer memory are going to go up far more than if we limited ourselves to a simple bag of single words. And just for the heck of it, we could do the same thing with a 5 gram. As is often the case, such decisions are trade-offs. The bigger the n in our n-gram, the more information from the original document we're maintaining, but we're also placing greater demands on our computer's resources and its processing power. Now, as long as I'm here, I'm going to go over and take a quick look at stemming and lemmatization. These are the 2 primary ways that we have of approaching the problem of words having multiple different forms. Stemming attempts to assign different forms of a word to some single root called a stem, but it's important to emphasize that stemming does not attempt to assign that root in an actual linguistically sensible way. All it cares about is that we're going to take 3 words like cries, cry, and crying and put them all in the same bin. The name that we assign to that bin is, in a sense, irrelevant. So let's go ahead and see what happens with stemming. I'll import the necessary Python libraries, and then I'm going to run using the Porter stemmer. This is a classic tool. Many people still use it, but it's beginning to show signs of age. Even Mr. Porter himself is researching newer and better ways of accomplishing the same task. But we'll go ahead and run it here. And one of the things we notice is that both studies and studying are reduced to STUDI. So we're putting both those words in the same bin. Similarity, cries, cry, and crying are all reduced to CRI. Once again, all being put in the same bin. But the bin itself has a name that does not correspond to any natural root or base word in the English language. Now, the idea behind lemmatization is we want to impose stricter criterion on the names of the bins. We actually pay a couple of prices for being stricter. In lemmatization, the root that you assign a word to is required to be an actual word in a dictionary. Many people use as their dictionary the WordNet database that was first created many years ago at Princeton University. So we're going to try that on the very same set of words. And now the results are English words, but the results are also not as good. Studies and studying are in fact put into two separate bins, even though logically they should be put into the same bin, and they were put into the same bin by the stemmer algorithm. So that's our trade-off. The stemmers tend to be faster and produce fewer stems, but when you're done, you don't have English words. Lemmatization is slower. I don't know if you noticed, but you could even see that when I ran that, it took a little bit longer, and we were just processing 5 words. But when you're done, you get actual words for the names of your bins. Now this brings us to the topic of word embeddings. That word embedding is a reference to some fairly heavy-duty theoretical stuff. We'll come back to that in just a moment. Usually when people talk about embeddings, they're talking about representing words as vectors. And the reason we say embedding is the theorists talk about a word being embedded in some abstract vector space. Now, the frequency-based embeddings arose from the original work done in the late 50s and early 60s in library science. Excuse me for a second. This includes the term leaned up against the touch screen again. This includes the term document frequency, which was developed by Hans Peter Lund actually in 1957. So that goes way back. The term document frequency, inverse document frequency, was introduced by Karen Sperk Jones in 1972. I'm going to take a quick peek at a term document frequency matrix. Have a fair amount more imports to do this time, and I'd like to call your attention to the fact that we are getting to the point where NLTK doesn't have enough muscle to do some of the things we need to do, so we're going to invoke the sklearn or scikit-learn library. And notice that what we're importing is TF-IDF vectorizer. That prefix there is term frequency inverse document frequency. So even though the techniques are modern, they trace their heritage back to the early days of computer document analysis. So we'll go ahead and do that import. And if I scroll down a little bit, I'm going to open up a file with, well, they call them documents. They're actually a set of sentences and phrases. There's actually two main points here. Number one is a document can be any set of words we want it to be. It doesn't have to necessarily be a page in Wikipedia or a technical manual or something like that. These particular sentences come from a paper published by Deerwester in 1990, and it marks another key point in the development of our technology. Deerwester was one of the very first people to take the term document matrix, which had been around for decades, and start treating it like a mathematical matrix. Instead of just an array in which we plug some numbers, Deerwester started doing things like attempting to do decompositions of that matrix in the mathematical sense. So this was the birth of text analysis, getting involved with matrix algebra. And we'll do what we have to do. My main goal here is to simply illustrate the term document matrix. And this, in fact, is a term document matrix. The columns represent our documents. In this case, there's only 8. You can see why we chose a small number of small documents here. The rows represent words that occur in those documents. So right now we can see that the word system appeared once in document 1, once in document 2, and 2 times in document 3. It's also easy to imagine that if we had a large set of documents, there's going to be a very long vector associated with the word system, and that vector is going to be mostly zeros. This is another problem that we're going to encounter frequently, and that we will in some way or another have to deal with. Right now, if we talk about a term document matrix, we're generally talking about very high dimensional vectors being associated with our words. Now let's think about that vector for just a moment. Let's imagine that instead of those sentences, these documents are just short phrases. And we might have millions and millions and millions of them. In a sense, the vector now becomes a kind of definition of the word. Think about how children learn words. Over time, they hear the same word used in many different sentences, except for a few very simple words like, mama and papa. Children pick up words by hearing them repeated again and again and again in slightly different contexts. Well, exactly the same thing is going on here. This vector is mathematically representing all the different contexts in which that word has occurred. And so becomes a kind of definition, if you will, of that word in our digital world. Now, I mentioned that the problem is that that's a huge vector. We need to make it smaller. People at Stanford University have used matrix techniques to reduce the size of that document. We're going to focus on something called Word2Vec. Now, even these techniques that we're going to be talking about in a moment, once again, have some serious drawbacks. One of the number one serious drawbacks of Word2Vec is that it treats all spellings of a word, it treats all words with the same spelling as the same word. But in English, we have words like lead, which is a verb. We also have the metal called lead, which is a noun. Word2Vec is not going to make any distinction between the two. Obviously, if you're trying to understand language, that's a critical drawback. More complex embeddings have been developed to kind of address these shortcomings. Elmo has been created to address what I just described, which linguist types call polysemy. In other words, a single word with, or what looks like a single word with multiple meanings. We'll talk about the remaining two on that list closer to the end. Now, Word2Vec was developed at Google in 2013. The idea behind Word2Vec is to find some way of taking a word and instead of being shackled to one of those 100,000 dimension vectors like we would be in the term document matrix, we want to reduce our problem to a much smaller one. Word2Vec does this with a neural network. However, it's a bit different than your usual neural network. On the input side, we have an input neuron for every word. On the output side, we have a neuron for every word. And I'm not real good at writing on this touch screen here. So just for argument's sake, let's say that there is 100,000 of them. In your typical perceptron-style neural network, you may have a hidden layer between the input and the output. In fact, you may have many of them. In Word2Vec, there's only one. But one of the characteristics about perceptron-style neural networks is that they're fully interconnected. In other words, on the input side, every input neuron is connected to every hidden layer neuron. There may be 300 of them. The same is true on the other side. Every output neuron is connected to by every hidden layer neuron. So that means that each of these neurons on the output layer is connected to by 300 hidden neurons. Now, what the heck does all of this mean for us? Most neural networks achieve their goal by looking at the output of that neuron and that neuron and that neuron. Maybe they allow us to classify, to say, okay, that bottle of wine came from that Italian winery. But here the neural network is doing a completely different type of job for us. We're not interested in the output weights once we've created this network. What we're interested in are the 300 inputs. Each of those output neurons represents a word. So each word is associated with a 300-dimensional vector that contains the weights from that neural network. Now, one very important thing we've accomplished is we put a whole lot of information in fewer dimensions, because in the term document matrix, it's all counts. 1, 2, 3, 10, whatever. Here, these are weights, 1.78, 1.625, etc., etc. So we've got a lot of information in a vector that's a lot smaller. 300 is a very common dimensionality for people to use when they're working with Word2Vec, though it's not at all rare for people to use 50 or 100 either. Now this brings us to GenSim. When Google created Word2Vec, they produced a set of code that would let you do things like encode sets of words, but their goal was simply to demonstrate the practicality of their concept. They weren't creating that code because they thought it would be a useful library for anything. They basically just said, okay, here you go, if you can learn from this, fine. But it wasn't a library. Since that time, other people have filled this void, Radim Rehuric being probably the most prominent. The GenSim library is very widely used because it allows people to use things like Word2Vec easily. So it's easy to use. It includes a lot of utility functions that allow you to work with very big files or streams of text data as opposed to files of text data. And it's not restricted to GenSim. It works with other types of embeddings like Stanford's GloVe. So GenSim is not a new technology in its own right. It's a library that has made existing technologies easier for the Python developer to use. Now, a concept that comes up very, very often in the world of machine learning in general is the idea that we have to achieve some sort of mathematical definition for what we human beings would call similarity. If we look at two photographs of faces, we can very easily say, yes, they're similar or they're different, but it would be very hard for us to articulate why we think two faces are similar, why we think they're quite a bit different. We have to approach this in a formal quantitative way. And very often in the world of text analytics, people end up choosing cosine similarity. And this is exactly the same cosine that you learned about when you had high school trigonometry. If we think about these words as being embedded in some abstract feature space, well, then it makes sense to say, okay, if this is the vector for that word, and that's the vector for some other word, what's the angle between those two vectors? Is it small? Is it large? Well, if the angle between them is small, the cosine of the angle is going to be close to 1. If the vectors go off in 90 degrees, in other words, if the words really don't have much to do with each other at all, then the cosine is going to be close to 0. And in fact, things can even move in the other direction. We could end up with a cosine close to -1. With the exception of scaling, this is exactly the same sort of math that goes into calculating a Pearson correlation coefficient in good old-fashioned columns of data from your favorite data analysis program. Columns of data can also be thought of as vectors, and the correlation coefficient is the cosine of the angle between those vectors, up to a correction for normalization. Here there's a diagram. It's actually surprisingly good if one considers that we're looking at 300-dimensional data. And of those 300 dimensions, we only get to plot 2 of them if we're trying to make it into a slide. But you can see that we've got a cluster of beverages up there. Here we have a bunch of meat products. Oops, I almost circled water. There's a bunch of geographical locations and so forth. You get the idea. If we've broken up words into groups that represent similar things, we can begin to get a handle on what those words are actually referring to. And this brings us to the topic of analogies. This is just one illustration of the sort of thing that you can do when you have created a definition for similarity. So I'm going to once again go back to the virtual machine here. I have run some of these in advance because we're getting into the area now where the files are fairly large and they don't run instantly like those few illustrations we saw a moment ago. But GenSim has a number of different related methods, including similar, and in this case, most similar. Okay, this is going to go into its vector data and determine which word is most similar to the keyword that I'm providing it with. So I'll go ahead and define that function. And if I scroll down a little bit, we'll try to do some analogies. Actually, I should probably do this one, not because it's particularly interesting, but because this is kind of the hello world of text analytic analogies. Notice we have man, woman, king. And if I run that, I get queen. In other words, man is to king as woman is to queen. And the GenSim figured that out on its own. Here's a slightly more complex one, but for me it was a little bit more fun. We're going to create a list of 5 different countries, and the idea here is US is to hamburger as some other country is to what? So we'll ask US is to hamburger as Australia is to what? And similarly, as Canada is to what? And let's run that and see what we get. The reason that I like this one is it surprised me. US is to hamburger as Canada is to poutine. If you've never been to Canada, this is one of Canada's comfort foods. There are street vendors selling it. Everybody's got their own recipe, but it's basically melted cheese and gravy over French fries. Okay, not really for the diet minded, but I think it's delicious. Okay, now this brings us to transformers. As we mentioned, one of the drawbacks to things like GenSim is it's only looking at the neighborhood of individual words. Like for instance, if you had a let's say a 7 gram, you're including the 3 words in front and the 3 words after. But that's all your data. You've got no information at all about words that are in the same document as the word of interest, but further upstream or further downstream. Transformers attempt to fix this with a technique that has come to be known as attention. As the transformer reads through the document, not only is it doing its step-by-step analysis, but it's also attaching weights to phrases that it encounters that indicate the potential importance of that phrase. If a phrase is encountered that is given a high weight, in other words, potentially worth paying attention to, then later on in the document, let's say the last sentence of the paragraph, the transformer can invoke information from the first sentence of that paragraph in order to make reasonable judgments about the text at hand. So today, as of September 21st, 2021, the transformers are basically the most powerful tool we have to approach text as a document in which one part of the document can affect other parts of the documents. We'd like to be able to do this with entire Wikipedia pages, but we don't have the resources and the processing power to do that. So transformers right now are our current best text. Some of the best natural language libraries use this technique. Google's BERT uses this technique. The T in BERT stands for transformation. And Baidu's library uses it as well. And just to show that Baidu has a sense of humor, when they open sourced their natural language processing library, they struggled to find an English algorithm that would correspond to the English name Ernie. So two of the most prominent natural language processing libraries on Earth both end up being named after Sesame Street characters. Okay, so there you go. Now, if you would like to pursue any of these topics, I'm a firm believer that the best approach is hands-on. It's like learning a foreign language. You can read as many books as you want, but you're not going to be able to speak the foreign language unless you go out there and try talking to some locals and see if you can get them to understand you. Well, it's the same thing with natural language processing on a machine. You've got to sit down and you have to develop a little bit of code. You can do that by getting samples to work with from a web. You can also do that by taking one of the Learning Tree hands-on courses. All of the Learning Tree technology courses all involve hands-on experience with lab exercises. Okay, so on that note, I'd like to turn things back over to Darby, see what she has to add.
Thanks, Dan. Thanks so much. We did have some questions during your presentation, and for those who haven't had a chance yet to ask your question, either publicly or privately, please do so. But in the meantime, I'm going to steal the stage for just one moment. For those of you who have participated in the past in webinars with or classes with Learning Tree, you'll be able to access this webinar on your My Learning Tree account. I know we had a question about that during the presentation. So for anyone who is new to Learning Tree, you also have a My Learning Tree account just by registering for this webinar. So in the next few days, you'll actually receive a follow-up email with details on how to activate your account and get access to this and other webinars, as well as other great assets like skills assessments and our e-catalog, things along those lines. So keep an eye out for your email. Dan, one of the questions that Paul and Adam actually they asked on the public board, so I'll say it there. They asked about will Jupyter notebooks be available, and I believe they're asking in regards to the follow-up materials on the My Learning Tree account. And if that is what y'all mean, I do want to answer that no, the Jupyter notebook portion will not be, or that app won't be available, but the slide presentation and the recording, of course, will.
Okay. Can I interrupt there for a moment? Can I interrupt there for a moment?
Absolutely.
Yeah. I actually am trying very hard to make these available but I seem to be in a perpetual state of behindness. In fact, I might as well just give up on the idea of ever being caught up. But these will become available. Probably the easiest thing is going to be to just post them on GitHub, but that has not happened yet. Okay, so if I post them on GitHub, I will let Learning Tree know, and I'm sure they'll figure out some way to mention that fact on the website. And by the way,
Perfect.
as long as I'm hogging the microphone, I wanted to make a comment to what Adam said. It would actually, I think, be fairly straightforward to marry this stuff to things like OWL and RDF, but not too many people are doing that because they tend to be different skill sets. I'm sure that most Python machine learning people have never heard of OWL. And to be perfectly honest, I have a soft spot in my heart for the Prolog language, which I think would be ideal for bringing these two different worlds together. Prolog fits in very nicely with RDF, and it would not be very hard for Prolog to read the same sort of text data that we're talking about here. Okay, I'm sorry, Darby, go ahead.
No, you actually, that was perfect timing because my Adobe Connect just froze, so I had time to close it up and come right back to it. So I apologize. Hopefully, I didn't miss anything in that. Or
Adobe Connect never freezes. It must have been sunspots.
Something happened. Okay, so I think you got to Adam's question, so that was perfect. And then a question that I had in my private chats was about you utilizing Linux for this webinar, and will Word2Vec run on Windows?
Okay. The reason that the virtual machine I use for this particular class is a Linux machine is that Google created its original proof of concept Word2Vec code to run on Linux. And it looks like it would be a nightmare to port it to regular Windows. But like I said, I don't think they ever intended it to be a library. So I wanted to be able to run that code just for comparison purposes. But if you're interested in using the techniques, the other libraries that have come out subsequent to that, including GenSim, they will run perfectly well on pretty much any platform that supports Python.
Okay, perfect. And then William is asking in the chat pod there, so you might see it. There's a bit of NN, neural networks, running under the hood. Does running on GPUs speed up the process?
I have not tested that directly myself. So I can't answer that. In principle, yes, but in practice, the developers who create this code do not always make the code GPU aware. So right now, my gut reaction is to say no. It could be in principle, but I don't think anybody's actually implemented that. But I don't know that for a fact. Maybe there is an implementation that I'm not aware of. But having said that, as far as neural networks are concerned, the Word2Vec neural network is a very, very simple one. It has lots of input and output nodes, but it's only 3 layers. And in the world of neural nets, that's sort of a cakewalk these days.
Okay. And then let's see, how much memory is required to run these algorithms on a real world data set?
Okay. Well, many, many years ago, the Duchess of Windsor said, you can never be too rich or too thin. If she were around today, she would almost certainly have added or have too much RAM. Uh, More is always better. The vector that I used for the GenSim analogy demonstration is from Google. It's a set of 300-dimensional vectors taken from Google News. The file is about 3.6 gigabytes. Um, it will not run on a 8 gigabyte virtual machine. Okay, it'll just crash Python. It will run on a 12 gigabyte virtual machine, but just barely. So that sort of gives you an idea of what we're talking about. I would regard 16 gigabytes as sort of the bare minimum for starting such a project. And, as I said, more memory is always better. But yes, it does take a fair amount of memory.
Okay. And Gary asked a question. Perfect timing, Gary. General question. Do you recommend newbies who are interested in machine learning take a math class to become more acquainted with various mathematic concepts?
Um, I think that that's a good idea, but postpone it a little bit. In other words, if you sign up for the math class um, first, you may just feel that you're learning lots of irrelevant details, and the math professors, unless you take a course specifically for math and ML, the math professors don't help. There was a very famous mathematician 100 years ago named Hardy, and he once made a toast where he said, "To pure mathematics, may she never have any application." And a lot of mathematicians have that attitude. So I would recommend playing around enough with the machine learning that you're beginning to get a feel for what's going on, and you're also beginning to come into contact with some of the mathematical terminology. And then when you take the math course, I think you'll be able to appreciate it more. If somebody starts talking about a stochastic gradient descent right off the bat, you're going to say, what the heck is he talking about and why should I care? But if you've worked on a bunch of neural networks and you've hit that term and you sort of get an idea of what it's all about, now when you go to the math class, you'll be able to appreciate it a lot more.
All right. Thank you. Great question, Gary. I thought that was a really good one. Thank you. And then we are hitting the top of the hour. I had one more question come in, maybe if you want to touch on it briefly. During data preparation, is it better to use a stemmer or to use lemmatization?
Well, the primary motivation for the stemmer is the fact that it's fast. However, people who are doing serious hardcore natural language processing don't want the added headache of having stems that do not correspond to actual words in the language. So the prevailing feeling seems to be that in this sort of natural language processing, better to spend a little extra time up front and then have a real set of words as your root words. I should also mention that remember that taking a whole bunch of documents and producing your word vectors is something you do very rarely. Once you create the word vectors, you can use them a lot for a great many different purposes. So probably better to spend that extra little time up front to get a better set of word vectors.
All right, Dan, thank you so much. And we are at the top of the hour, so I'm going to go ahead and wrap this up. But if you have any questions, please don't hesitate to reach out to Learning Tree either via phone or email. We're happy to answer your questions for you, and we'll look forward to hopefully seeing you again soon.